Yeah, so it's my pleasure to welcome Professor Yasser Shokri from UC Irvine, and his research is very interesting and very close to a lot of the work that we do at Penn. And his focus is on resilient control systems, and he's going to talk about the formal methods and the verification aspects for these learning-based systems. And Yasser, like we were just discussing, he's had worked with many of the leaders in cyber physical systems, like Sanjit Seshia, George Papas, Manish Srivastava, and Paolo Taboada. And so welcome, Yasser. It's welcome you back to our lab at Penn. And we'd love to hear on all the new things that you're doing.
Thanks a lot, Rahul, for the very nice introduction. And it's really nice to come back to UPenn, at least virtually for now. So today I would like to discuss with you some of my group's work on this intersection of formal verification, machine learning, and so on. So I believe by now everyone knows that machine learning is amazing. You can do a lot of really interesting stuff related to autonomy, training neural networks. Right now, anyone can train a neural networks. Even high school students right now can train neural networks. But still we have some challenges that we need to face, especially when it comes to the safety of the use of these neural networks and how much we can trust these very deep neural networks, these black box neural networks, and so on. So here is a couple of examples. So this Tesla, here it is in the self-driving mode. Someone is calling it to come to him. And as you can see, although this is a very perfect situation, the sun is shining, there is no object in front of the cameras, everything is perfect, yet the decision-making inside this Tesla was about to take a wrong decision. Same story in the bottom video, same situation now. It didn't stop correctly in the stop sign. It was going to crash with the other car. And in the literature, in the news, everyone, and then you will see more and more of those situations about the lack of safety and lack of guarantees associated with these machine learning techniques. So the challenge that we have been trying to do for the last 5 years is how we can systematically design neural networks that are provably correct, that are guaranteed to be safe, that are guaranteed to give you some sort of assurance. What kinds of new theories that we need to develop to assure the performance of these neural networks? Can we come up with algorithms, scalable algorithms that can design such provably correct neural networks, and how we can implement these provably correct neural networks in different real-life situations? So an overly simplistic vision of machine learning is just this box. You have some data, you have an objective function, and you use it to come up with some neural network weights. Okay, whether this is a reinforcement learning or imitation learning or any kind of training algorithm, at the end, this is what machine learning provides to us. Some objective function, some training data that was collected from an expert or collected through an interaction with the environment. At the end, we would like to come up with some neural network weights. Instead, let's take a step back. And in many of the cyber physical systems, we have some imprecise model of the system, of the dynamics governing our system in the form of a differential or a difference equation. And we have some system level specification. I believe most of you guys are expert in temporal logics, or at least have heard about temporal logics, linear temporal logic, signal temporal logic, and so on. If you are not very familiar, just think about some way of formalizing what do you want the autonomous system to do, like avoid these obstacles, go here. Every time you see someone coming, you have to stop, some high-level specification. And now the question is how we can take this imprecise model along with the specification and blend them in the training to get some neural network that is provably correct. The first question, even before we start training the neural network, how can we come up with the architecture of the neural network? So if I give you some data and I ask you to train a neural network to do some control task, should you use this architecture with 2 hidden layers and I don't know, 5 neurons in each layer? Should you use 3? Should you have more neurons in one of the layers and less in the others? Well, we don't know. And so far, the state of the art in neural architecture search is let's try all of them. Let's try one, train it, evaluate. If it works well, good. If it doesn't work well, let's go pick another one and just iterate. And this is very dangerous, especially when it comes to autonomy. Why is that? Because in autonomy in general, you are going to face new scenarios, new parts of the data that you have never seen before. So maybe you are evaluating your trained neural network on data that is collected from a certain part of your state space. And once you fix the architecture of the neural network, this architecture is going to place some hard constraints on the function that is represented by this neural network. So for example, if you use a shallow neural network with 3 layers in this case, then this neural network will always add this hard constraint, regardless of how much you're going to train it. This function, because of the architecture itself, every time you put some neurons, it is adding some implicit constraints on how the function that you are, the neural network is representing. You are restricting its class to a particular class. It is usually very hard to understand what is the class of functions that you're restricting yourself by picking a particular architecture. So instead of just trying to use data to evaluate and train, what we have been trying to do is what we call as a formal neural architecture search, where you give me the dynamics of your system, you give me the system level specification. I will give you a neural network architecture that is guaranteed to have an assignment of its weights to make it correct. I'm not going to give you the weights of the neural network, but I will tell you for this architecture, there exist weights for which will make this neural network always generalize well. Once you have an assurance on the architecture and you know that I'm using the right architecture and which gives me there is a hope to generalize, the next question is how we can take this neural network architecture and try to train this neural network. And this is what we call neurosymbolic neural network training, which is going to be the focus of my talk today. Basically, what we would like to do is, while training the neural network, we would like to restrict the gradient descent evolution of the weights of this neural network, of the neural network weights, such that at the end, after the training, this neural network represents some symbolic object that I can deal with, that I can understand, I can check its properties and so on. So for example, while training of a neural network, I can guarantee at the end of the neural network training, I don't understand what are the weights out there, but I can give you an equivalence between this neural network and some finite state automata, for example. Finite state automata, we can understand its safety properties, we can understand its reachability properties. It is easy to understand. And this is the objective of neurosymbolic training, which I'm going to discuss in a few minutes, but let me just complete the overall picture of what we have been doing in my lab. So after you come up with an architecture, after you come up with a neural network that have some symbolic representation, the next question is you'd like to verify the neural network. You can verify the symbolic representation of the network. Sometimes not. It is hard to come up with symbolic representation for all different neural networks. So sometimes we have to go and verify the neural network itself. Either you verify the neural network in isolation, or you'd like to verify the entire closed loop behavior. These are completely two different problems that sometimes depending on what is the properties you're interested in, you may need just to verify the input-output behavior of the neural network. Sometimes you may need to verify the entire closed-loop behavior of the neural network. Verifying the neural network, the input-output specs of the neural network is an NP-hard problem, and we have been working with some heuristics in order to relax the problem, in order to achieve some good performance, basically using different kinds of heuristics. But on the other side, we can also find neural network architectures for which the verification problem becomes polynomial time. So the verification of input-output characteristics of neural network in general NP-hard, but we were able to find two architectures for which it is actually polynomial time in the number of neurons. So as you make the number of neurons inside your neural network gets bigger and bigger, these architectures, you can verify them in polynomial time, and that's why we can get like 400x execution time decrease by exploiting these the properties of these structures and so on. Once you can verify the input-output characteristics of a neural network, now you can try to verify the closed-loop behavior of a dynamical system. And we have done it for two applications so far. One of them is vision-based autonomous landing, where you have an aircraft equipped with a camera, and you have a neural network that processes the images of this camera and try to control the aircraft to land safely. And another one where you have lidars, and the robot is working in workspaces that have some nice properties and so on. I will not go through the details of these verification problems, but I'm just giving the overall idea. If you are interested in any of those topics, please let me know, and I can discuss with you more offline about these topics. Once you verify the neural network, you may find some concrete counterexamples, places for which the neural network is going to fail. And now the question is, what do you do? You can either go and try to just retrain the neural network, or in some cases, you may try to change the neural network as little as possible, because the neural network is doing well most of the time. It is just in certain areas where it is taking wrong decisions. So you'd like to change the neural network as little as possible so that you keep wherever the neural network was working well will remain well, and just fix the parts for which the neural network is failing. And this is what we call the neural network repair. Sometimes you may be able to do that. Sometimes you have to go back and train the neural network. After you go through this entire process of coming up with the architecture, training, while having some guarantees on the training, verifying and repair, at that point, you can get a formally verified neural network. There is a lot of open questions underneath each of these blocks. We have been we are just scratching the surface on most of them, but there are a lot of other work to be done in all of those blocks out here. For today, I'm going to focus on the neurosymbolic neural network training. So the problem we are interested in is as follows. So you have your most favorable robot that you'd like to control. Maybe it is a quadrotor out here, and you'd like to design some neural network that can control this robot. You go to your simulator and you start playing with reinforcement learning or imitation learning or whatsoever. At the end, you get some neural network that can move your robot very well inside this environment and can satisfy the mission goal that you are interested in. But now you need to use this neural network to control a completely different quadrotor, which doesn't exactly follow what you have in the simulation. You need to control it in an environment that is completely different than the one that that was trained on. And then finally, the goal itself, the mission and the goal that you are interested in is completely different. And this is what inspired people to look into meta-learning in general, which instead of trying to train a neural network that is good for only one task, you would like to train neural networks or train some agents that can generalize to tasks that were not considered during the training. By task, it can be a difference in the dynamics of the robot. It can be a change in the workspace. It can be a change in the mission goals or whatsoever. Anything that is different than what you used for training. And there have been a lot of different techniques from meta reinforcement learning, domain randomization, transfer learning. There's a lot of different techniques that were proposed in the literature. However, the challenges with these techniques, they usually lack a formal guarantee on that they will actually be able to generalize in simulations and experiments. You may find some scenarios for which it generalize, some other scenarios for which it may not generalize. It is not clear when you will be able to generalize, when you will not be able to generalize. You don't have these formal guarantees. You don't have formal guarantees in terms of the safety of the neural network, that it will always take right decisions, that will not hit an obstacle, for example. And you come up with this very black box, deep neural network that you cannot interpret. And the objective of this research is how we can come up with new techniques that for meta learning that can guarantee to generalize for unseen tasks, safe, as well as have some notion of interpretability. So we have two extremes out here. One of them is the classical control theory. From classical control theory, the controllers we get are guaranteed to be safe, guaranteed to generalize for different mission specifications, for different, you can bound if your error have certain, the difference between the dynamics you use for design and the actual dynamics have some, is bounded, for example, you can still guarantee that what you did in simulation or in your laptop will generalize to the actual system. But usually these problems become computationally intensive, especially when the dynamics of the robot become more complex. And you need a lot of assumptions about access, what kind of models you can use, some assumptions about uncertainty and so on. On the other extreme, on the other side, we have learning-based techniques. You can achieve amazing performance, empirical performance in a very computationally efficient way. It can be used for very generic nonlinear systems without knowing the exact equations of the dynamics out there, but they usually lack formal guarantees. And what we would like to do with this neurosymbolic framework is how we can bridge the gap between these two extreme methodologies, how we can use some ideas from symbolic control and abstraction-based control to help getting better learning algorithms, and how we can use learning algorithms to come up with a better control theoretic approaches. For today, I'll just focus mostly on the upper arrow, which is how we can come up with ideas that bridges, that take some results in formal methods and control theory and implement them inside machine learning so that we can have neural networks that are guaranteed to be correct. So the exact problem formulation, you are giving some nonlinear dynamical system that is composed of two components, F and G. F is your nominal dynamics, which is a black box model. You don't know exactly what is F. You have access only to a simulator, for example, for which you can query F. And then G is the error between the nominal model and the actual robot, which you don't know at the training time. You'll only know it at the execution time. But we assume that this G in general can be learned through a Gaussian process regression. So for different robots, you may have a different GP that represent the error between the nominal model and that particular robot. Now, we would like to train a feedback neural network controller. So the neural network controller that we would like to design takes the state X as an input, produce the control action U. And we would like to make sure that when you use this neural network to control your robot, then you are satisfying some safety and liveness properties. It can be generalized for bounded linear temporal logic or CoSafe LTL. For now, I'll just keep it simple and just focus on reach avoid problems. So you would like to make sure that you are avoiding obstacles while getting into the goal of interest. So, and we would like this neural network to be able to generalize to any workspace, any set of obstacles, any LTL mission bounded linear temporal logic or CoSafe LTL, any model error, and you don't know any of them during the training phase. So during training, all what you have access to is the function f, and you don't know the workspace, you don't know the mission, you don't know the error, you don't know the obstacles, and you would like still to be able to generalize to all of them. So our framework is as follows. So during training, we are going to train a library of neural networks. Each of these library of neural networks will have some properties that we are going to ensure during training. And then during execution, once you know the task, once you know exactly the workspace and the mission and the model error and so on, we are going to create this switching network, which is going to take the library of neural network and start composing them such that you come up with a composition that is guaranteed to satisfy this task. Once you have another task, you will start composing these neural networks in a different way to satisfy this task. To do that, we need to have to make sure that every neural network in our library is by itself correct or have some property. And then we'd like to make sure that the composition between these neural networks is also correct. So let me explain a little bit more about these two steps. But before I go there, let me make sure that we are all on the same page in terms of the problem statement and the general idea of the framework. Is any questions before I move forward?
Any questions, guys?
So what is the sensor information? What kind of sensor?
So in this, for now, I'm just, for simplicity, I'm assuming the state. So you have some sensors that are measuring the state because the neural network takes as an input for this presentation just takes the state. Okay, and I'm assuming for this presentation that the state, I have a perfect measurements of the states. And it can be generalized once you start having noises over the states and what's not.
Yeah, so just so you know, there's coffee here and there's Chipotle lunch if you want to have some.
Okay.
For you too, Yasser.
I'll do it virtually after the
Yeah, so feel free to take, and if you have more questions, keep asking.
Okay, if no more questions, let me talk about the training of the neural networks. So first recall that every neural network, when you're using ReLU activation units, it is nothing but a continuous piecewise affine function. The architecture of the neural network and the weights are going to give you different CPWA functions, but all of them, nevertheless, all the neural networks, once you start using ReLU activation units or any of its variants, it is nothing but just a continuous piecewise affine function. So this means your neural network is nothing but just some linear function in the state X, but this linear function is going to change from one state to another. Okay, depending on your training, at the end, you will get some different linear functions that are activated in different portions of your state space. So if we assume that the space of all piecewise affine functions out there is polytopic and bounded, so I'm going to call this P, this calligraphic P out here. This is the space of all CPWA functions that belong to a particular polytopic bounded set. The first step is I'm going to take this set and I'll start partitioning it into what I'm going to call controller partitions. So if my state X have the dimension of the state X is 3, the control action is 2. So this means I'm for every X, I will get some linear function that is just mapping 3 to 2. Okay, so this is like a matrix. I can start giving some bounds on each of the elements of this matrix, and this will give me what I'm calling controller partition. So P1, for example, says that I have some CPWA functions, but for the first element of this of the matrix, all the CPWA functions for this in this element belong to a certain range, for example. Now, I will go to my nominal dynamics F, and I'll start using some techniques from abstraction-based control, where in classical abstraction-based control, you have you discretize your state space as well, and you ask the question: if my robot is in state Q1, which is the gray box, I'm going to represent this as this entire portion of the state space. I'm going to represent it as one state in a finite state automata, or an MDP in this case. So let's take the probabilities out of the way just to make it simple. So whenever the robot is in the gray box, I will represent this by saying now my robot, the state of the robot is inside the circle Q1, which is a finite state automata. Whenever the robot is at Q2, I will represent this by another state in the finite state automata, and so on. And using the nominal model of the dynamics, which you have access to, which is a simulator, you can ask the question: if I have a CPWA function within the controller partition P1, where I will end up being. So for example, you go to your simulator, and from there, you know, if my robot is in Q1 and I have some CPWA function that belongs to P1, I will end up either at Q2 or at Q4. And these kind of techniques have been developed in the abstraction-based control. They are usually developed for concrete control signals. And what we did out here is we generalize it for a CPWA, for a set of CPWA functions. I will not go through the details. It is just a small amendment on what people have already developed in the literature. But at the end, using the nominal model, I can build this symbolic model, which says if I am at Q1 and I apply some CPWA function within P1, I will end up either at Q2 or at Q4. If I apply a CPWA function out of the family P2, I will end up at Q2 or Q3, so on and so forth. I can do this using my nominal model. Now, I would like to train a neural network. I would like to train a neural network for each of those families, P1, P2, P3. And I would like to make sure that after the training, my neural network is guaranteed to represent one of the CPWA functions within this set. Of course, if you use traditional training, imitation learning, or reinforcement learning, or whatsoever, you cannot have this guarantee. So after you do your normal gradient descent training, we introduced a projection operator that takes the neural network, project it to the closest function within the set P1, for example. This projection operator takes the weights of the neural network and try to find how can I change the weights of the neural network as little as possible, such that all the linear functions inside the neural network is within the set that is called P1.
Question?
Go ahead.
So why go this way? Because you are starting from a random set of controllers and then figuring out what they do, and then you're refining them. But if you already have a desired set of behaviors as the finite state automaton that you showed, and you could do this projection, why not start here?
So the projection takes a neural network, gives you a neural network.
Right. So if you could do that, I mean, in your previous slide, you had the state space, right? The finite state automaton.
Yeah.
So if you knew that P1, like if you knew your desired behaviors from Q1, where to go Q2, Q4, and Q3, and I could, let's say, do this projection with some degree of flexibility, then I would just build my neural networks to do that. Why start from something, try to project it, and then go into this loop? Why not start here?
So during the training of the neural network, you can select the data to belong to P1, for example, and you try to fit on data that is coming from P1. In practice, this does not eliminate, but reduces the amount of time you need to do the projection. But still, by just collecting data from P1 and train a neural network, you don't have a guarantee that it is actually belongs to P1. And the entire question that we're interested in is how to come up with a formal guarantee that of the entire framework. So you can start with a neural
data from Q1 to Q2.
Say it again, sorry?
you don't have enough data for these transitions, you're saying?
Even if I have data for these transitions, I suppose I have millions of data for these transitions from Q1 to Q4. I use all this data to train a neural network. What is the guarantee on the neural network that it is actually representing P1 and there exists no point at which the neural network is not representing a function within P1? Right? In practice, yes, but formally that's the question. And this is why you need the projection. From our experiments, yes, when you have a lot of data, you don't need a projection. Like whenever we do the projection, it returns exactly the same neural network. Sometimes even we have a huge number of data, it have to change the weights very, very slightly to ensure it is within P1. So this is what the projection operator gives you. It gives you a guarantee, a formal guarantee that the neural network is actually representing some CPWA function within P1. You don't know which one. It depends on the data. It depends on the objective function, for example, of the reinforcement learning that you are using. At the end, you'll get one function within P1. Okay. Does this answer your question?
Yeah, we can go forward.
Okay.
Why do you model the automata?
Can you raise your voice? I can't hear you.
Why do you model your automata as a non-deterministic version?
So this is classical in all of the abstraction-based control, because this set P1 is not just one function. It is a set of multiple CPWA functions together. So some of them will take you to Q2, some of them will take you to Q4. But P1 is a class of multiple functions coming together. So it does not always take you to a one particular state. Depending on where you are in Q1 and which function you use, you may go to Q2 or to Q4. Okay? Okay. And the good news is this projection is a linear program, so it is efficient to compute. And we can bound the difference in terms of what the projection is doing in terms of the changes to the control signals before and after the projection. Nevertheless, at the end, what you have out here is a library of neural networks. And each of these neural networks is guaranteed to represent a CPWA function that belongs to a certain family. So regardless of the numbers of the black box behavior of the neural network, regardless of the weights out there, I can always treat each of these neural networks as a CPWA function that I don't know, but I know for sure it belongs to one of the families P1, P2, P3, and so on.
Question.
So this,
I'm sorry if I missed it. How did you get the library of neural networks? How did you train them?
So
or what were the objectives that you trained them for?
So I will go to this finite state automata. For each of the arrows out here, I'm going to train a neural network and project. So for Q1, I am going to train a neural network and project it on P1. I'll train another neural network using the same data that is available to me, projected on P2, use the same data and project on P3 and so on. Then I will do the same for Q2, for Q3, for Q4. So for each state in my abstract model, I will train a neural network and use the projection operator to project it on one of those families until I have all the possible combinations.
So your projection is a refinement step, basically.
It's a refinement step. Usually you need to alternate between training and projection. So you train, project. It's like a projected gradient descent. Okay, you don't need it to do it every single gradient step. You may use multiple gradient steps then project. As long as your projection is the very last step in your training, then you have the guarantee that the neural network represents a CPWA function within this family.
Okay, so you do start from your abstract states and train them.
So the abstract states, I can get it from the knowledge of the nominal model. And then now I have my data or I have my reinforcement learning reward or whatsoever. I start training and I project.
Right. So you start from the abstract states and then go this and then start this one. Okay.
Yes.
That was my question.
Now you have this library. Another question? Am I hearing another question? No? Okay. Now once you have this library of neural networks, now once you know the task, you know what is your workspace, you know what is the mission, you know the model error, which is the difference between your dynamics and the nominal dynamics and the actual robot, which we assume to be a Gaussian process. Then you go back to your finite state automata. You use this Gaussian process to take this finite state automata, turn it into a Markov decision process, where now you can integrate over the Gaussian process and so on to get the probability of these particular transitions. At the end, once you have the model error, you can transfer this finite state automata into a Markov decision process with some probabilities. Once you have the mission that you're interested in, for example, I would like to go to Q4 while avoiding Q2, for example. So I can just use the finite state automata, or the MDP in this case, and try to use dynamic programming in order to know what are the transitions inside this MDP that maximizes the probability of satisfying my task. And this is something that have been studied very well in the literature of formal methods in general. So, and this is once you know like the transitions inside your MDP, all what you need to do right now is to select the right neural network that is guaranteed now to take you through this transition. You have, thanks to the projection operator that we discussed, you have a one-to-one mapping between the transitions on the symbolic model out here and the neural networks. And now it is easy for you to select which neural networks to activate at which part of the state space. And this is what we call the switching network. Once you have another task, you are going to just change your switching network and so on. And now things become very easy because we have this one-to-one mapping. And it is easy now to give some formal guarantees on this framework. So you're given your nonlinear system that is composed from F and G. F is your nominal model that you use to come up with the symbolic model. G is your error. You train this library of neural networks. And now you can guarantee that the probability between this composed neural network to satisfy the specification minus the compared to the best possible CPWA controller is bounded. So think of all CPWA controllers that are out there. We can guarantee that the composed neural network is not very far away from the best possible CPWA controller that can achieve this mission in terms of the probability of achieving the mission. So this, in other words, if the mission is achievable, if there actually exists some trajectories that can achieve this mission, then with high probability, our controller, this composition of neural networks is guaranteed to satisfy it. There are certain different practical considerations that you can have that we allude to in our paper. Like, for example, we don't need to train the full library of neural networks. Actually, we can come up with some transfer learning algorithms that again use the projection operator that I discussed in order to say I have neural networks, a partial library of neural networks. When I look into my task, I found that I don't have neural networks that will take me through certain transitions in my Markov decision process. So what can I do? Go to my library, pick one that is as close as possible to the transition that I'm interested in, apply the projection operator. Now I have a neural network without any data, without any retraining. I have a neural network that is guaranteed to belong to another family of CPWA functions. So I started with one that belongs to P2, and without any data, without any retraining, I'll just solve a linear program. And now I have one that is belongs to P1. And you can still have the same exact theoretical guarantees in terms of the probability of satisfying your mission. And if you have, you can even accelerate this process even more if you have data from previous. So remember, when we started, we said, I don't have access to any tasks at all. I don't have data from any tasks. But if you have data from some tasks, you can use them to accelerate the training of the neural network library, as well as the construction of the symbolic model, the MDP. I'll not go through these details, but you can find them in the paper. Let me give you some examples. So here is an example We picked this particular example because there is a recent paper by Dorsa Sadiq's group at Stanford that says that if you train your neural network on one of those workspaces, it is impossible to do transfer learning of these trajectories and generalize to the other tasks. The reason out there is you need you cannot do continuous morphing of these trajectories to satisfy the other tasks, and this is called homotopy classes. So these workspaces belong to different homotopy classes, and it was shown that techniques from meta reinforcement learning will not be able to generalize for this kind of tasks. So if you train on the third workspace out here, you cannot generalize to the rest. And here is an example. So on the top, you can see the trajectories from our controller. And in the bottom, you see the trajectories from one of the meta reinforcement learning algorithms. So on the top, we train on the third workspace, and we can generalize for all the 4 workspaces, thanks to the ability of composing smaller neural networks together in a correct way to come up with the right trajectory. While on the bottom, as you can see out here, using techniques from meta reinforcement learning on the workspace that is similar to the one that was within the same homotopy class of the one that was used for training, which is the third column. The trajectories are safe. You can avoid the obstacles while getting to the goal. While for the other workspaces, because they belong to different homotopy classes, you cannot generalize. Here is another example. So we have this robot working in this lab, and then suddenly my student will go and change the workspace. Again, although we didn't have some of the neural networks that can take us through this right turn that we had out here, we can, in real time, we can update our library to come up with the neural networks that are missing in our library, and then we can start activating them in the right fashion, and we can adapt to these changes in the obstacles and so on. Any questions so far? All right. So this is just a general overview of the framework. There's a lot of mathematical underpinnings that I try to abstract away, like how you deal with the probabilities of your coming from the Gaussian process, how to bound these errors and so on. But this is the generic idea of how we can use ideas that were developed in the formal methods community, like the symbolic abstractions and so on, and we can apply it to machine learning. And the main concept that allowed us to bridge these ideas was this projection operator that allows us to reason about neural networks as a function that belong to a certain family of functions. We can do the other way around. We can use techniques from reinforcement learning and imitation learning to accelerate the process of the algorithms in formal methods like symbolic abstraction-based control and so on. But I will not go through these details. Let me know if you're interested. We can talk more about it. In the last few minutes, I would like to show you some other work, which is related to, well, most of like the main power of neural networks come when you are using some vision-based control. And in all the talk I give so far, I have been focusing on state feedback. So I don't have a vision sensor, for example. So we don't know still how to generalize our results into neural networks that can, to general neural networks that can do vision. We were able to do it for specific situations, like as I talked earlier about the autonomous landing of aircrafts. We can reason about the vision in this scenario, but in general, it is very hard to reason about. So instead of trying to come up with a neural network that is verified, let's say that we will always have a neural network that is unverified, but can I augment it with a filter that is going to take the control actions coming from the unverified network and try to project it to the closest safe action that out there. So you can think of this from a control theoretic point of view. You can think of this as something similar to control barrier functions, for example, but on neural networks. In the reinforcement learning arena, it is called shields. In control theory, it is called barrier functions. At the end, the concept is the same. You have some controller or some neural networks that you cannot verify the question, or you don't know its properties. How can I come up with a safety filter that can filter out the unwanted control actions? So, of course, there is a question of how you can do it for vision and so on. I'll not go through the details, give you just directly the results. So out here, we have a neural network that is poorly trained, that will not be able to guarantee the safety of the neural network. And then we're going to add this filter that is formally verified to be safe. And this filter is going to filter out the unsafe actions. And this is what you can see. The poor neural network is always trying to hit the obstacles, and then the filter tries to intervene, takes it away, and guarantee that the overall system, although you have some part that is unverified, the entire neural network is guaranteed to be always safe. And using this is what we call root of trust network. Using this root of trust network will even help you during the training if you have access to such a network. Of course, the question is how you can come up with this network, how you can come up with the architecture of this neural network to guarantee that it can implement a safety filter, how you can train it to make sure that it is actually a safety filter. And this is exactly what we provided in this paper. For ground robots, we give you a neural network with the right architecture, with the right weights, that is guaranteed to work as a root of trust for these kind of problems. So this is the overview of the framework that we have been trying to develop, how we can come up with architectures that are correct, how we can use ideas from symbolic control into the training, how we can verify the resulting neural networks, and how we can repair neural networks that are that have some problems for which have some counterexamples and so on. So let me stop out here by thanking my students and postdocs. I was just presenting their work. This is mostly all their ideas, and I'll be happy to take more questions. If you'd like to delve more into some details here or there, let me know. I'll be more than happy to discuss. Thank you.
Questions. So Yasser, for the first part, do you have any runtime component that is checking, or it's just correct by construction?
The neurosymbolic part, this one?
Yeah.
Yeah, it is correct by construction, because we are composing the network at runtime. So this composition, the red box, happens at runtime. Once we know the task, we are going to compose the neural networks in a way that is guaranteed to satisfy the task. You have a new task, we'll do a different composition and so on, but the composition is correct. Of course, there is a question of what happens if the workspace is changing over time. We didn't address that problem. So the assumption here is once you have a task, once you know the workspace, it will remain fixed until you finish the task. After you go from point A to point B and the robot is at rest, maybe the workspace will change again and will start again the composition of the neural networks again. But during the execution of the task, the workspace and the mission and everything is constant.
So, I mean, a follow-up to that. So LTL-based planners have been around for a long time, at least for these abstracted states, automata-based planning, right?
Mm-hmm.
So how does, I mean, the box in the blue, it makes sense. It can be a neural network. But for the components in the red, how does it compare with the standard LTL-based planners, which just use things like maybe probabilistic tools or even deterministic tools like RRTs and stuff like that? Did you compare, or what's your comment on, like, why not use a standard technique once you've abstracted away the dynamics into automata and then just plan with those? Because those would be more runtime. They're flexible enough that they can be changed in runtime, and you can do You can do a lot with them because there exists a lot of work with
Yeah.
planning in these
Yeah,
domains.
the main difference is as follows. So for classical LTL-based motion planning, you discretize the workspace and you discretize the control space, right? So if your control actions can take a value from -5 to 5, you take this control action and start splitting it into small pieces, right? And each of these control actions will represent one of the transitions inside your finite state automata. Here, instead of discretizing the control action, the space of control actions, we are discretizing the space of controllers, of the control functions. So this gives you a much smaller set to play around with. So if you have from -5 to, if your control action is from -5 to 5, and now you are going to discretize it with 0.1 discretization step, you get a huge number of control actions. And now the transitions inside your finite state automata is going to be big. And this is why these techniques does not scale very well for complex systems. What we have out here by discretizing the space of controllers instead of the space of control actions, you will come up with smaller number of partitions, and each of these partitions will allow you for a more complex controller to be implemented out there. So if you think about, take this neurosymbolic framework and push it to one of the limits where this controller, the discretization of the controller space was pushed all the way to the limit, so that each of these controllers P1, P2, P3 represent only one control action. Now you will retrieve the LTL-based motion planning. If you push it to the other extreme, where each of these, you have only one controller partition that have all the CPWA functions out there in the world, you will retrieve back the reinforcement learning or the neural network training, because when you are training them, you don't know which CPWA function it can pick any CPWA functions out from there. So this is somewhere in between. That is, you are allowing the neural networks to take out some of the complexities about the dynamics. You don't need now to reason about every single control action in the set of all control actions that you have. You allow the neural network a little bit of flexibility to change the control action as long as it is within a particular set. And so because now,
why not switch among the controllers? I didn't mean to discretize the control space. My question was, why not switch among the different controllers using the LTL-based planning?
So,
what's the comment on that?
So you mean how we are composing the neural networks together, right? So the composition of the neural network is more or less using some techniques from the abstract-based control. So once you have this abstract-based finite state automata, we'll run the existing techniques out there in LTL-based planners. When you run it on this finite state automata out here, will tell you, I need to take a transition that is labeled by P2, followed by a transition labeled by P1, followed by a transition labeled by P3, for example. Okay. Now you go to your neural network library and say, which one of you guys represent a transition that is labeled by P1? This one? Okay. So this is the neural network that will be executed out here. This will be the neural network executed there, and so on. Okay, so analyzing the finite state automata itself, we didn't do anything new. We just use the techniques from LTL-based motion planning on this abstract model. But remember, this abstract model is different than the abstract models in the literature, because the abstract models in the literature, the labels of the transitions are control actions. Here are families of CPWA functions. Okay. So once you solve this, you don't know what to do. And this is where the neural network comes to play. Okay, the neural network say, I am a CPWA function that belongs to P2. I can be used to guarantee this transition out here.
Right. So So my question was, the box in red is your planner which uses LTL.
Is my planner, yes, which is a normal planner, a normal LTL planner. Once I do the planning, I will know the transitions that I need to follow. I will replace these transitions with neural networks, with the corresponding neural networks. And this switching network out here is nothing but activating the right network in the right place.
Oh, okay. So the neural network on the red box is just a choice. It's not. It's not a planner.
Yeah. You see the inputs that are coming to this network are the outputs of all the other neural networks. So it's just selecting which control action I will pass to the actual road. So think of it as a switch or a multiplexer, for example. Okay, in this state, I will take this neural network. In this state, I'll take this neural network. Okay.
I have another question about composing these neural networks.
Hmm.
So let's say you take neural network 1 and do something, and you complete an edge in the automaton, and then you want to complete the next edge, for example, right? Now the distribution of start states from which you would have trained the second neural network may not match the distribution of states you reach, for example, right? And what if the neural network 1 reaches this abstract state, but it so happens that it always reaches in an unfavorable state for you in order to continue?
Yeah,
right? Is this something that is handled by the assumptions on the abstract states itself? And if that is the case, then how would you remove this assumption?
Yeah, so this is part of the math that I try to abstract in the presentation, but this is one of the concrete problems that you need to that we addressed in the paper, but I try to remove this complexity in the presentation. So the model error that you have out here is assumed to be a Gaussian process. Okay, so this means for each of the states you have a different Gaussian distribution. So when you have this finite state automata, you can go to this Gaussian process and start annotating these labels with probability, transition probabilities. You go to your Gaussian process and say, okay, this now will be probability 0.3, this will be probability 0.4, and so on. It will not just give you this probability 0.3, it will give you a range. It will use this transition. It will take a range from 0.2 to 0.4. Okay, it is guaranteed to be within this range, and this transition will be within this range, and so on. And now, when we are doing, when we are solving our dynamic programming on top of these transitions, we need to take the worst case possible transitions out there, so we can guarantee that our controller is correct. And this is, oops. So in this, in the formula out here, on the right-hand side, the very first component, which is H, which is your the number of transitions you need to take. And as this number of transitions starts to go longer and longer, your probability of satisfying the specification will start to go down. Because now, because with every single transitions, you may be taking an unfavorable, go to unfavorable state and so on. And this is where appears here in the bound. But remember that when you go to that other state, there is another neural network that will try to push you back to the original trajectory that you were trying to get. So this is where the math starts to be complicated, and this is the final formula of what you get. The delta on the very right-hand side of the inequality, this delta superscript nn, is capture the worst case range of probability transitions, and this is where you can go. So yes, it is inside the math, but I try to abstract it away.
So my question is, so within an abstract state, you are somehow assuming that you might be able to have a small delta for all states within it, and they are somehow similar in terms of what will happen in the future. And if that's not the case, I guess
is not
you know, to refine the abstraction further, right?
So it is not the same in the future, because the Gaussian process is going to be different from one state to another. So in one state you have a Gaussian distribution, another state you have a completely different Gaussian distribution. Okay, so this is what's captured by the Gaussian process, but we assume that we know the Gaussian process. I knew this GP, which represent these errors in the dynamics, and this gives me a way to predict what is happening in the future. I think what you are alluding to is, what if I don't know this distribution and there is a distribution shift in the future that I have no idea about, right? This particular case is not handled because we are assuming that I know the entire Gaussian process everywhere on the state space. So this means at any point of the state, I know what is going to be the probability distribution from that particular part of the state space. I have this full knowledge. Make sense?
Okay, thanks. Yeah, that.
Any final questions? And any questions from people online? Great, Yasser, thank you so much. This was very interesting. And
Thank you for having me.
I'm sure there will be many questions following afterwards also. So thank you
Yeah.
so much.
Sure, I will be more than happy if you're interested in any of the pieces, either the one I presented or the other ones, please let me know. I'll be more than happy to jump on a Zoom call with you.
Thank you. Let's give Yasser a